Okay, hello everybody. We're pleased to have Carl Rodriguez with us today. Carl got his BA in physics at Reed College in Oregon and his PhD at Northwestern University. He then became a Pappalardo postdoctoral fellow at MIT, followed by an ITC postdoctoral fellowship at Harvard. And since 2020, he's been an assistant professor at Carnegie Mellon University. And Carl is one of the leading theorists looking into the formation of black holes in dense stellar environments using novel computational techniques. And today he'll tell us how to make a binary black hole. So welcome, Carl.
Great. Well, thank you, sir. Thank you very much. And thanks everybody for having me out. I'm sorry that I can't visit in person, but fortunately we're all, for better or worse, we're all, I think, getting pretty comfortable with Zoom talks and Zoom colloquy at this point. So first of all, just to make sure that everybody can see these slides, but I always like to start off with this slide in particular, because it really sort of emphasizes just how dramatically our understanding of black hole astrophysics and particularly stellar mass black holes have changed over the past just 5 years alone. So this is the picture of everything we knew about stellar mass black holes, those that are typically born from the collapse of massive stars, circa 2015. So pretty much from the first detection of SIG X1 all the way up until 2015, pretty much everything we knew about stellar mass black holes, we knew through observations of X-ray binaries. That is, a black hole orbited around by a companion star is stripping some of the gas off of it and emitting a lot of hot X-rays from the accretion flow onto the object. And we had a pretty firm understanding, we think, of what all of these objects actually, of what sort of the parameter range of these objects was. In our own galaxy, they had masses anywhere from 5 to 15 times the mass of the sun. There had been a couple of tentative detections of things more massive than that, but those were relatively poorly constrained due to some of the very difficult systematics with measuring these systems. But anyway, what I'm getting at is that this entire picture changed in September of 2015, specifically with the detection of the first binary black hole merger that we detected through gravitational waves, GW1904. And right off the bat, this system already shattered some of the things we thought we knew about stellar mass black holes. We're already observing two black holes merge that are more massive than anything we had observed in the local universe or in nearby galaxies. And we're seeing them produce a black hole that is significantly more, that is nearly a factor of 4 more massive than anything we'd observed in our own galaxy. As of late last year, the whole picture had exploded to look something like this. And I really just like to leave this as a sort of intermediate slide to where we are now. And with the release of the LIGO and Virgo collaboration's second gravitational wave transient catalog, the picture now looks something like this. We now have more than, we now have about 50 detections, depending on how you want to cut off marginal detections, of binary black hole mergers observed only through gravitational waves. And just to really hammer home exactly how much this has transformed the field, at this point, the majority of stellar mass black holes that we have observed in the local universe, that we have observed in the universe, have been observed through gravitational waves. The majority of information that we now have about black holes, and particularly binary black holes, now comes from gravitational wave astronomy. And of course,
is there significance to that, to the x-axis there?
The x-axis is just arbitrary. It's just ordering them in whatever way makes the plot most aesthetically pleasing. The y-axis is solar masses, so it's the particular mass of the events. You have the components that are then being fed into whatever their merger product is. And so right now, the name of the game is LIGO and Virgo, the two second-generation gravitational wave observatories that we're all familiar with. But they're not, of course, the only gravitational wave observatories that are operating. The pulsar timing arrays have been collecting more and more data, adding more pulsars and more observatories for at least a decade now. And they're getting to the point where within the next few years, a detection of supermassive black hole mergers and gravitational waves is very likely. Circa 2030s, we will, knock on wood, see the launch of the Laser Interferometer Space Antenna, essentially giving us a new window onto larger black holes, 10 to the 5, 10 to the 6 solar masses, the kind that reside in the cores of galaxies. And even further along down the line, in the 2040s, we might start seeing the next generation of ground-based observatories come online, things with names like Cosmic Explorer or Einstein Telescope. And if you look at the design specs for these new generation of observatories, some of them are suggesting that they might be able to detect stellar mass black holes out to beyond redshift 10. For those of you that are familiar with star formation history of the universe, we really don't think there were a lot of stars forming at redshift 10, and certainly not with enough time for them to evolve and collapse to be black holes. So there's a non-trivial chance. This statement has a bit of theorists' bravado in it, but not nearly as much as you might expect. There's a non-trivial chance that by the 2040s, we might be in a position to observe every black hole merger everywhere in the observable universe through gravitational waves alone. And so that's where I like to start these talks off, because it really sort of sets the scene and also sort of gives you an idea of how radically this field has changed over the last 5 years, when we've gone from essentially a pre-data era where it's just a bunch of theorists doing our theory thing to now standing almost on the precipice of a deluge of information, where we're going to start to be able to really constrain the theory space, both in terms of formation scenarios for these binary black holes and in terms of the astrophysical environments that they form in. And so that brings me to sort of the title slide of this talk, which is just sort of how do you form a binary black hole in the first place? Because believe it or not, we are actually still not sure where the majority or even many of LIGO's binary black holes are coming from. We still have essentially a large oversubscription in theory space that is preventing us from being able to identify specific binary black hole mergers and their gravitational waves with particular theoretical predictions. And so I'm going to start off and describe sort of the two main channels that people typically talk about when they're talking about forming binary black holes. And then I'm going to go on to talk a little bit more about one of these two channels, which I've done a fair bit of work on, and also how I think we can potentially discriminate between different formation scenarios as LIGO collects even more and more data. So getting to the actual formation scenarios for binary black holes, like I said, there's typically two general pathways that these general categories that these formation scenarios fall into. In the first, you start off with a massive stellar binary. This is relatively easy to do from an initial conditions perspective. Most of these stars that we observe, and particularly the massive stars, have at least one massive stellar companion. But if I start off with a massive stellar binary with a sufficiently large separation, in this case about 20 times the Earth-Sun distance, or 20 AU, you can form a binary reasonably easily through what we think are the normal processes of stellar evolution. So in this case, the massive primary of the binary goes supernova, or directly collapses with no explosion, leaving behind a black hole. The secondary, as it processes through its hydrogen fuel, eventually will expand onto the giant branch, increasing dramatically in radius with a very diffuse, very low density hydrogen envelope. And eventually, if the binary separation is just right, that envelope is actually going to envelop the primary, leading to what we call a common envelope phase of evolution. In this particular phase, what we think happens is that the core of the secondary, the degenerate core of the not degenerate core, but the core of the secondary and the black hole primary shrink in this envelope due to dynamical friction, a form of dissipation, and essentially bring the orbit into a significantly closer separation. That siphoning of energy from the orbit is injected into the envelope, causing it to be ejected out into space. At this point, the core of the secondary continues its normal evolutionary process and collapses into a black hole. And if you tune this just right, you start off with just the right initial separation, you have the right density and entropy profiles for your common envelope, you can end up with a binary black hole that stops just before merger, but close enough to where gravitational waves can bring it to merger within the age of the universe. As you can imagine, this channel can explain all of LIGO and Virgo's observations and can explain several order of magnitude more events than we actually observe. But the real problem is one of fine-tuning. You have to really understand very well the very difficult gastrophysics of this common envelope phase and several other phases of evolution that we really don't have a good theoretical or observational handle on. The other way to form binary black holes is to dispense with the pre-existing binaries entirely. So you start off with two massive stars. They have no separation problem whatsoever, so they can just evolve on their merry way, leaving behind two sort of black holes. But then you have a second problem, because now you have two unbound objects that you need to get somehow or another into a bound system. If I just throw these two objects at one another in the field of a galaxy or in a star cluster, right? It's a, positive energy in, positive energy out. There's no way to create a bound system from a two-body encounter, at least not Newtonian gravity. And I'm going to get back to that assumption in a minute. But if I expand the number of objects in this interaction from two bodies to three bodies, then I can actually have a far richer sort of available set of outcomes to me when these encounters occur. In particular, if I allow a third body to be nearby during the two-body encounter, I can essentially dump the excess in energy and angular momentum of that two-body encounter onto the third body, creating a bound system. And the third body just carries away some of that excess energy. Now, as you might imagine, these sort of three-body encounters where you have three objects within a close enough radius that they can both form a binary and carry away that excess energy and angular momentum are very, very unlikely in the low-density environments of galaxies. We think even over the entire Milky Way's history, over all stars, this has probably happened ballpark 100 times over a Hubble time. But if you look in different regions of space, and in particular in the cores of dense star clusters, what you'll actually find is that you end up with regions with a very high number densities of black holes. And in that case, it actually turns out that these type of encounters can occur extremely frequently. This is what we typically call dynamical formation scenarios. Now, like I said, I usually try to describe these two sort of competing channels in sort of broad categories. In reality, there are a whole host of different binary black hole formation channels. I'm listing just a handful of them here, each of which has different mechanisms for bringing the two black holes together, to combining them into a binary, to causing them to merge over, to bringing them close enough to where gravitational waves will actually cause a merger. A handful of, at least one formation scenario doesn't even depend on black holes originally sourced from collapsing stars. The real problem is that we have all these theories. What we want to know is there some way we can actually discriminate between these different theoretical formation scenarios? Can we actually tell the difference between binary black holes and their formation environments based on predictions from theory and how they match up to specifics of the gravitational waves? And that's what I'm going to talk about for probably the next 20 to 30 minutes. But before I get to that, I'm just going to briefly describe how black holes actually form and interact within these star clusters. So a pretty good sort of first approximation to a lot of star clusters that we see in the Milky Way, things like globular clusters or some superstar clusters that we see in nearby galaxies, is to imagine just a single gas cloud, a single giant molecular cloud that fragments and forms anywhere from 10 to the 4 to 10 to the 7 stars, essentially right at this, essentially all at once. So imagine an entire litter of stars born in a single burst of star formation. Now, after that star formation is complete, this is a very idealized picture, of course, but after that star formation is complete, the most massive stars will rapidly go supernova or collapse to leave behind a population of compact remnants. And this happens relatively quickly after the stars begin their lives on the main sequence. Ballpark about 10 megayears, depending on the mass of the stars. Now, at this point, I have sort of a classic problem from collisional stellar dynamics. I have a massive object traveling through a sea of low mass stars, where the entire set of interactions are controlled by gravitational two-body encounters. For those of y'all that have done any sort of plasma physics, it's essentially the same kind of physics that we get in the Boltzmann, that you sort of get in the Boltzmann approximation. But in this case, what I can imagine is that I have this massive object traveling through the sea of stars. It's going to attract each of the lower mass objects to it. And as it moves as it moves to the right with some velocity, it's essentially going to build up a wake of objects behind it, essentially creating an overdensity of objects behind the direction of travel of the massive particle. In this case, the end result of this is that it actually causes these massive particles to rapidly spiral into the center of their clusters. Because as the black holes travel through the sea of stars, they're essentially experiencing an acceleration in the -v direction, causing them to rapidly spiral into the center of their clusters. This happens, the timescale for this depends on the mass ratio between the stars and the black holes and and the overall size of the cluster. But for most of the clusters we see in the Milky Way, this process takes ballpark 100 meg-years, or maybe a few hundred meg-years. Fun side note, this is one of the only forces I know in sort of classical mechanics where the acceleration of the object itself also depends on the mass of the object. So the force goes as the mass squared, but the acceleration actually depends on the mass as well, because the size of the wake you build up depends on the mass of the object. And so at this point, I've essentially driven all of the stellar mass black holes into the center of this cluster, where I can suddenly get a very high spatial density of objects. And at that point, we can start to actually talk about forming binaries through three-body encounters. Now, this can happen relatively quickly, but it turns out that once I create the binary, it's not necessarily close enough to where it will merge within the age of the universe. Just because I've created a binary black hole doesn't mean it's close enough to emit gravitational waves and drive a merger. And so the way to look at this is to actually imagine, in a way, a particle physics experiment. So I have a three-body encounter. It's created a binary black hole that is hanging out in the center of this star cluster. You can essentially imagine this as having a target with a cross-section that is ballpark the semi-major axis squared, being continually bombarded by particles from the rest of the star cluster. If you really want to show off to your field theory friends, you can actually parameterize the available encounters in terms of the total energy and the sort of output and the possible outcomes. In reality, these aren't actually modeling any sort of perturbation. You can't really do calculations with this in any particularly useful way. And because unlike field theory calculations, we are actually just solving Newton's equations, it turns out to be much easier to just do this on the computer. And so the best way to visualize this is to actually just to see what happens when I throw an interloping essentially beam star at my target and sort of watch what happens numerically. And so in this case, I have single interloper comes in, interacts with the binary. It's going to undergo several sort of close encounters with the binary until eventually what you'll see is that the interloping star actually ejects one of the two pre-existing components of the binary. And if you look closely, you can actually see that something else pretty interesting has happened there as well. In addition to exchanging one of the binary components, you can pretty easily see, even just by eye, that the orbital separation between the newly formed binary is smaller than the orbital separation of the binary that went in to the encounter in the first place. And you can actually show that on statistical average, as long as the sort of relative velocity of my star and binary is lower than the orbital velocity of the binary, on statistical average, that is always going to be the outcome of these types of encounters. This is something called Heggie's law. Essentially, binaries that are more energetic than the typical stars in the cluster will characteristically shrink their orbits, liberating some of the gravitational binding energy of that binary and transferring it into the recoil of the binary center of mass and the single interloping particle or exchanged particle. And so after this encounter, the binary shrinks. That to conserve energy, of course, that energy has to go into the recoil of the center of mass, and the binary is kicked out into the halo of the star cluster. Once it's out there, dynamical friction brings it back into the center, and the process happens again. And this happens again and again, each time characteristically shrinking the binary and sending it onto a further excursion out into the halo of the star cluster. When I say halo, by the way, I don't mean dark matter halo. It's an unfortunate confusion of terminology. I really just mean the outer regions of the star cluster. And so after each one of these encounters, I essentially have a competition between two separate physical effects. I have the gravitational wave merger timescale. That is, how long is it going to take gravitational wave emission to drive this binary to merger? And I have the typical timescale between successive binary encounters, which you can calculate just with a simple n sigma v type argument. If the gravitational wave merger timescale is significantly less than the typical encounter timescale, then eventually the binary is going to merge inside the star cluster before it interacts with another interloping particle. On the other hand, if the gravitational wave merger timescale is much longer than the typical interaction timescale, eventually one of these encounters is going to be sufficiently energetic that it actually ejects the binary out of the star cluster entirely. It's relatively easy to push these objects with enough recoil that they actually completely escape the star cluster to begin with. Once the binary is outside of the star cluster, it may or may not merge later on in the galactic field that the star cluster inhabits, just depending on what the properties of the binary were when it was ejected from the star cluster. One neat sort of side effect of this is that even though this is a formally chaotic process, it's the gravitational 3-body problem itself embedded in the gravitational million-body problem. It's a formally chaotic process. But because the limiting factor here is just the gravitational wave merger timescale, which we can calculate with a simple integral, and whether or not the binary recoils with a velocity greater than the cluster's escape speed, it actually turns out that you can make pretty good predictions for what the sort of minimum semi-major axis that dynamics can drive this binary to before it either begins to merge or is ejected from the cluster. And so it's actually the escape speed of the cluster that determines the properties of most of these binaries, despite this being a formally chaotic process. And so a higher escape speed means you have more in-cluster mergers, but you can still make pretty good predictions for exactly how many you're going to get and how many will be ejected out into the field of galaxies. And so you can even write down, if you're particularly interested, a nice sort of log normal distribution for what the typical separation of binaries are when they're ejected from the cluster as a function of the size of the cluster itself. This is from some paper that I did as part of my PhD. And as you dial up the number of stars in the star cluster, getting a higher a deeper gravitational potential and a higher escape speed, you essentially push the typical separation of binaries to smaller and smaller values. And so that's one of the really nice things of dynamical formation scenarios. There are no appreciable dials or free parameters. It's all well understood gravitational dynamics. Once I start with some initial conditions, once I start with some positive stars and population of black holes, it's all well understood deterministic Newtonian dynamics. There's a couple of caveats to that statement I'm sure has popped out to many of you, and I'm going to discuss both the Newtonian assumption and conditioned assumption a little bit later in the talk. And so getting back to the initial question I asked, which is, can we tell the difference? I want to look a little bit more about the various predictions from these different formation scenarios. Now, initially, this was circa 2016, we all had a few ideas for how you might be able to discriminate these various binary black hole formation scenarios. We thought you might be able to use things like masses or the merger rates or perhaps the mass ratios between the objects. Say if one black hole was 10 times bigger than the secondary black hole, then that would be pretty suggestive of only a handful of scenarios. But the problem is it turns out that there's a lot of overlap in these three parameters in theory space, and that a lot of different theories can essentially produce enough similarity in these three quantities that it makes it very difficult to sort of constrain things that way. And so that's out. I'm gonna sort of change the question a little bit to something I focused on a little bit more in my postdoctoral work, which is instead of can we tell the difference based on astrophysical observables, is there some way we can tell the difference based on specific relativistic observables in the gravitational waveforms themselves? In this case, I mean things like the black hole spins and their orientations with respect to the binary, or the eccentricities of the black holes at the time of merger. Are they purely circular, or is there some non-circularity that imprints itself on the waveform? And finally, I'm going to revisit the question of black hole masses, because it turns out that spins actually couple to black hole masses in an interesting way that I'll discuss in a little bit. And so focusing on these three observables, I'm going to go through them one at a time. And I'm going to start with the eccentricities. And so just real quick before I get into that, I'm going to mention how we actually model these. I'm only going to mention this at the one slide level. But essentially we use, for modeling these dense star clusters, we actually use a statistical technique that is based, again, on a sort of statistical approach from plasma physics. We are actually computing the first and second diffusion coefficients directly from what's called the Fokker-Planck approximation. And then we are actually essentially using the sort of statistics of that to model how orbits of stars within the cluster change over time due to nearest neighbor collisions. And then we're just randomly sampling these orbits in their Newtonian potential. The nice thing about this is, whereas the gravitational in-body problem, say 1 million bodies, can still require months or even years to explicitly calculate with direct force integrations, with this sort of mean field, not mean field, but with this sort of statistical approach, we can model a cluster with 1 million particles with only a day to maybe a week of computer wall time. And because we're doing it on a star-by-star basis, you can add as much additional physics as you want. So in addition to two-body encounters, you can add strong encounters between binaries and single stars using a small N integrator. You can add stellar evolution prescriptions. You can basically add as much additional physics as you want. And like I said, we've shown that this statistical procedure can reasonably well reproduce the effects, the sort of outcomes, the sort of cluster models that you get from direct in-body integrations. I'm showing on the left just sort of the radius enclosing the radii enclosing various mass cluster in sort of spherical shell, based on comparisons to a direct in-body integration of 1 million particles. And again, to emphasize this, that in-body integration, this was sort of state-of-the-art circa 3 to 4 years ago, took 13 months on a massive GPU MPI cluster, whereas we were able to reproduce essentially at the half mass radius, which is sort of one of the sort of key indicators of a cluster's radial extent, within 2 days of computer wall time. And I'm happy to talk in much more detail about that sort of afterwards, but I prefer not to get too much into the nitty-gritty of in-body simulations. But going back to gravitational wave observables. So remember how I said earlier that to create a bound binary in the Newtonian approximation, you need a third object, right? Because you need some way to dissipate some of that energy and angular momentum of the two-body encounter, and some way to dump that excess energy and angular momentum. Now, like I said, in the Newtonian sense, you need a third object. But in the relativistic case, of course, gravitational waves themselves are a dissipative process from the system. If I emit gravitational waves, I am essentially subtracting energy, at least from the two particles that are orbiting around one another. And so in this case, I can actually replace in a post-Newtonian sense, this third object with the emission of gravitational waves itself, and essentially create a binary during a two-body encounter. And so to show you what I mean by that, I'm going to play the same movie that I had before, the same three-body scattering, but this time I've added relativistic corrections to the equations of motion. Specifically, I've added, paracenter precession, but I've also added the 2.5 pn relativistic correction, which essentially allows for radiation reaction from the system. And so what you'll see now is that you get a bunch of very close paracenter passages. The black holes are coming very close to one another until eventually two of the black holes come so close to one another that even on the time scale of this encounter, which is probably only a few, I think for this one, of years, that these two black holes appear to emerge almost instantaneously. Now, if I zoom in on that process, it's not actually instantaneous. What I'm going to do here is now show the last sort of 90 days of these two black holes, right from the point where they form a binary to their first paracenter passage, all the way up until merger. On the top, I'm going to show just the sort of binary itself. On the bottom, I'm actually showing the gravitational waves that are etched out in real time from this encounter. And so right off the bat, what you see is that every time the two black holes undergo a very close paracenter passage, you actually get a huge spike of gravitational waves. You don't see the normal chirp gravitational wave that you've sometimes seen in other talks. Instead, you see just a single pulse of gravitational wave emission right at paracenter passage. And so what happens is the binary circularizes and very rapidly is driven to merger within, in this case, less than 90 days from the point of formation. And if you look at this, very carefully, you can see that these two objects are still not entirely orbiting around, are still not entirely on a circular orbit. In fact, if you form these things with a close enough paracenter passage, and you drive them to merger very, very quickly with an initially very large eccentricity, you can actually retain some of that eccentricity all the way up until merger, when it can be detected in the gravitational waves themselves. Now, we were not the first group to realize this. I think the first people to look at post-Newtonian dynamics and these kind of encounters goes all the way back to the mid-90s. I think the first people to really point this out for its applications to LIGO were really initially Cole Miller in the early 2000s. It was revisited and sort of revamped by Johann Samsing and Enrico Ramirez Ruiz. And then our contribution to this, which we put out a couple years ago, started to look at exactly how often and what masses you expect to predominantly produce these effects within globular clusters. And so to sort of emphasize what this does to the gravitational observables, what I'm showing here is on the x-axis, the orbital eccentricity of the binary black holes once the gravitational wave frequency, or the peak gravitational wave frequency, crosses 10 hertz, which is roughly speaking the lower limit of detectability for LIGO, or the beginning of the LIGO sensitivity bucket, as they call it. And so for primordial black hole binaries, which in these simulations is how we refer to stellar mass, or to pre-existing stellar binaries that undergo common envelope evolution, the majority of systems are going to merge with eccentricities of 10 to the minus 6. They're essentially going to be circular. But if I look at the entire distribution of eccentricities from globular clusters and from other kinds of star clusters, I get a distribution that looks much more like this. And in fact, essentially a trimodal distribution. The first peak is dominated by binaries that are ejected from the cluster, and eventually may or may not merge many gig years later in the galactic fields. The second peak is those objects that merge inside the cluster. This actually turns out to be a bit of a selection bias, because essentially higher eccentricity means you merge faster. And so if you have a higher eccentricity at some point, your gravitational wave merger timescale is much lower, and you're much more likely to merge before you're kicked out of the cluster. And then this third peak at just under 0.1 is these gravitational wave captures. This is what happens when you include relativistic corrections to the otherwise Newtonian equations of motion during 3-body and 4-body encounters. LIGO can ballpark begin to measure deviations from a circular orbit that have eccentricities of about 0.1 or greater. And so it turns out that from these star clusters, something like 5% of all mergers should have detectable eccentricities inside the LIGO-Virgo band. There's a second sort of interesting fact about this, which is if I incorporate the gravitational wave emission, both in terms of the isolated binaries that merge the cluster and these gravitational wave captures, I find that roughly half of all the binaries merge inside their star clusters. That's for star clusters with typical escape speeds typical of most of the globular star clusters that we see in the Milky Way. And so eccentricities, it turns out, work as a discriminant. What about the spins of the binary black holes? And so what I mean by spins is actually going back to essentially spin-orbit coupling, but in this case for binary black holes, instead of the quantum version that I think most people are more familiar with. And what I mean by that more specifically is the following. Imagine I have a binary black hole that is initially aligned, both of the components have some intrinsic angular momentum, some intrinsic spin, and that spin is aligned with the orbital angular momentum of the binary. And so this sort of cartoon version at the point of merger is going to look something like this, the waveform that I have sketched out on the right. What I'm going to do now is slowly rotate the spins into the plane of the binary such that they're at 90 degrees with respect to the orbital angular momentum. And as I do this, what you'll notice is that the gravitational wave on the right begins to shift. Not only is there a huge frequency shift, but you actually start to see these amplitude modulations in the waveform itself. Those amplitude modulations actually come from the spin orbit, from the precession of the binary about the total angular momentum. Essentially, the spin orbit coupling of the individual component black holes to the orbital angular momentum causes the entire system to apparently precess around the total angular momentum. And gravitational waves have a higher luminosity if you're looking at a face-on binary than an edge-on binary. And so it essentially is encoded into the waveform as these amplitude modulations. Now, unfortunately, LIGO, because one of the best ways to do sort of analysis for the signals is actually by template subtraction, where you go through with very long waveforms and subtract them from the data. It turns out that LIGO is not very sensitive to amplitude modulations in the waveform. What they are very sensitive to is frequency modulations. If the frequency is very slightly mismatched, you can detect that very easily, whereas a mismatch in the amplitude is much harder to observe. And so if I continue to rotate these spins until they are anti-aligned with the orbital angular momentum, the amplitude modulations disappear, but I've got a huge frequency shift in the waveform. And that is actually what LIGO can detect very, very well. And so if I look at astrophysically what I expect the spin orbit alignments to be from various formation channels, I get a lot of information just from my basic understanding of how these binaries form in the first place. So if I start off with the massive stellar binary picture, if I assume that the two stars are essentially rotating in the same direction, which is not an unreasonable assumption, though there are some caveats to that. But if I make that assumption, then the only thing that can significantly misalign these stars from their orbital angular momentum is the actual supernova itself. If you imagine that a supernova ejects material preferentially in one direction, which we think it does, at least for neutron stars, based on the observations we have of pulsars that are just sort of roaming around the galaxy with very large velocities, then the only way you can really misalign the spins in the orbit is to essentially torque the binary. So you have a supernova explosion, it torques your binary angular momentum. The normal process of stellar evolution continues after this, but if you assume that the black hole and stellar spins are essentially gyroscopic, they're essentially going to keep pointing in the same direction regardless of what I do to the pre-existing binary. And so the primary way of creating spin-orbit misalignment from isolated binaries, we think, is through these supernova explosions. And so for the most part, you're limited in the size of your supernova explosion. Eventually, it's going to be the velocity kick is going to be so large that it'll completely disrupt the binary. And so for the most part, you expect the spin-orbit misalignments to be, they can be somewhat large. I mean, they can be almost all the way up to 90 degrees, but you don't expect a huge number of them to be much greater than 90 degrees. Even in the most optimistic assumptions, you can only expect maybe 10% of the binaries to have some amount of spin-orbit misalignment that's greater than 90 degrees. On the other hand, for these sort of star clusters, the spin-orbit alignments are going to essentially be isotropic. You're forming these things in a formulaic environment. There is no reason for the spins to be aligned in any particular fashion. You essentially get your standard, sine theta or cos theta, depending on if you want latitude or co-latitude distribution for binary misalignments. And so our real idea with this was that you could use essentially the projection of the spins onto the orbital angular momentum, a value that is typically called in post-Newtonian parlance the chi effective parameter, as a way of discriminating between these two formation scenarios. Essentially, isolated binaries should mostly positive chi effective parameters. Dynamically formed binaries should roughly have 50% aligned, 50% anti-aligned. And so a lot of us wrote quite a few papers about this, looking at how this varies as a function of mass and how many events you would need to sort of discriminate these different scenarios. And then at least up until 2002, the second LIGO observing run, it seemed that most of the binary black holes had chi effectives near zero, which could mean they're all at 90 degrees lying in the plane, or it could just mean that black holes don't have large spins to begin with. And so we had to contend with the question, what if most black holes have low spins? What does that actually tell us what would that actually tell us about the formation scenarios? And would that have any unique implications for the formation scenarios? And the answer is yes. And that sort of gets me to the third bullet point up here, which is the masses. So remember how I said that for your typical star cluster in a Milky Way, most of these binaries about half of these binaries are going to merge inside their star clusters. And when they do, you're going to essentially create a new black hole with a mass that is a little bit quite the sum of the two progenitor masses. You lose a little bit to gravitational waves. And with a spin, a dimensionless parameter of around 0.7. The thing is, if you assume that the spins of black holes that are born from stellar collapse are all near 1, so they're essentially spinning as maximally as possible, which is what we assumed pretty much until we started getting gravitational wave observations, then it turns out that the merger of two black holes imparts a significant recoil onto the remnant black hole. In this case, it can, even for circular binaries, this can be up to 5,000 kilometers a second. And for typical mergers inside globular clusters or lower mass star clusters, they'll still be around 1,000 kilometers a second. That effect essentially arises from asymmetric emission of gravitational waves. If there were no spins, right, this would be a purely axisymmetric system. You would not expect a preferred direction for gravitational wave emission. But if you have a particular spin-orbit misalignment, you can actually create a significant, essentially emission of gravitational waves and the momentum they carry in a preferred direction. Since the escape speed for these clusters is typically maybe 10 to 100 kilometers a second, most of these binaries would go flying out of the cluster. But if what LIGO tells us is right, and it turns out most black holes born from stellar collapse have no spins, then that gravitational wave emission is essentially isotropic, or actually axisymmetric, and you essentially get no net kick. And so the recoil kicks can be as low as 0 kilometers a second. In reality, they depend on the mass ratio as well, because that's something else that breaks the asymmetry. But for typical binaries merging in a cluster, something like half of them will be lower than the escape speed of their parent star clusters. So if I have half of my binary black hole mergers occurring in star clusters, and half of those remnants staying in the star cluster, essentially I'm going to have a generation of much heavier black holes that then return to the center of the star cluster, find themselves another companion, and potentially merge again. We typically refer to this process in terms of generation of stellar mergers. So the black holes born from collapsing stars, we typically call first generation mergers. Those born from repeated mergers, or at least the mergers of two black holes, we typically call second generation black holes. So this would be a 1G plus 2G binary black hole merger. And so how many of these second generation mergers I see depends obviously on what the birth spin of black holes from stellar collapse is. But as a function of that birth spin, I can answer the question of what fraction of mergers are expected to be have at least one second generation component in them. And it turns out that more than 10% of mergers from these star clusters should have at least one component that was created in a previous black hole merger, if the birth spins are 0. If the birth spins are, say, 0.1 or 0.2, this fraction decreases. But even then, even if the spins are as low as 0.2, I'm still seeing that around 4 to 5% of mergers should have one component created in a previous merger. Now I'm going to skip ahead a little bit because I know this is only supposed to be 50 minutes and I don't want to go too far over time. But one of the interesting things about this is that if I look at what sort of the maximum mass of black holes is, it turns out that there's a pretty good reason to think that there's a maximum black hole mass that you could get from stellar collapse, above which you essentially cannot form black holes from collapsing single stars. And so what we're looking at now is essentially the total intrinsic merger mass of binary black holes formed from common envelope evolution, from massive stellar binaries. This is from a paper by Chris Belchinski. And what he's showing is the effect of introducing a new bit of physics called pulsational-pair instability supernova. Essentially, we think that any star that would end its life with a black hole core mass above about 40 solar masses, give or take, there's some debate about that number, should undergo these essentially violent pulsations, essentially ablating the outer regions of the core until you're left with a black hole that is about 40 solar masses. Anything above about 60 solar masses and the thing just completely detonates in a supernova explosion that leaves no remnant. And so, at least for isolated binaries, we think that there should be a maximum total merger mass of about 80 solar masses, so 40 plus 40. On the other hand, if I look at the distributions from star clusters, and I plot this same quantity on the x-axis, that total intrinsic merger mass, suddenly, from star clusters, I'm getting a whole host of objects above 80 solar masses. And they're largely dominated by second generation black hole mergers, where one of the components was created in a previous merger. And so if I block off this region here, what I'm essentially looking at is something called the pulsational-pair instability gap, where we think you can only realistically form black holes and black hole binaries through repeated successive mergers of black holes. So we've been talking about this for a while, and then lo and behold, middle of 2019, LIGO detects this object, which was then announced on September of last year. And they were able to infer that the primary black hole mass lies within the gap produced by pulsational-pair instability supernova. That GW190521 has a primary mass of around 85 solar masses, which strongly suggests it could only be produced through some successive merger of black holes. So if I look at the posterior probability distribution here, the vast majority of the primaries probability, it lies within that pulsational-pair instability gap. And not only that, the spins have strong evidence for being large and in the plane. In other words, the spins are at about 90 degrees as far as we can tell, to the orbital angular momentum. Itself, also another strong evidence of dynamical formation. But not only that, there were even a couple of papers that came out after the initial announcement from the LIGO-Virgo collaboration that suggested there might even be eccentricity in the gravitational wave signal itself. This is from a paper by Romero-Shaw et al., where they found that there's essentially strong support for this binary black hole entering the LIGO band with a gravitational wave frequencies with a eccentricity greater than 10 hertz, or excuse me, an eccentricity greater than 0.1 at 10 hertz. If I compare that to the eccentricities predicted from our paper in 2018, that lie right around the peaks that you would expect from gravitational wave captures. So overall, this one event suggests a strong evidence of dynamical formation. And with that, I think I'm at the 50-minute mark. So I'm just gonna put everything back on this original slide. Thank you all so much for tuning in, and I'm happy to stick around and answer any questions anybody might have.
Thank you, Carl. I think we can unmute our microphones and give him a round of applause for a nice talk. And are there any questions for Carl? If you have a question, you can raise your hand on Zoom, and then just going to call on you, or otherwise you can type your question in the chat. So I have the first question. There's just a clap in there. So I just have a first question to get the discussion going. So this latest detection you talked about, you said there's evidence for the spins being on the plane, and before you said that there was small recoil if there was no spin, but is the recoil also suppressed if the spins are perpendicular to the angular momentum?
Well, no. So if the spins are at 90 degrees, that actually produces a relatively powerful kick. However, at this point, it wouldn't matter. So if this was a dynamically formed binary black hole, say it was formed through successive mergers, the first generation of mergers, where you form the 80 solar mass black hole, has to have low spins. The second generation not only can have large spins, it in fact has to, because that orbital angular momentum of the first generation binary essentially gets put into the spin angular momentum of the remnant. So they should have spins of roughly speaking 0.7, depending on the mass ratios, and they should be at least with a cosine theta distribution, should be essentially lying in the plane. Now, I should point out that there's one thing I slightly oversold there, namely that it's very, very difficult to model, and we don't currently have a good gravitational wave template for spinning eccentric binary black hole gravitational waves. And so the studies that have looked at this have either looked at, there are two studies. The Romero-Shaw one, I believe, used non-spinning gravitational wave, they used a gravitational wave template that has eccentricity, allows for moderate eccentricities, but only allows for aligned or anti-aligned components of the spins, so it can't model anything in the plane. The other study that I know did this, and I'm blanking on the first author's name, I think it was like Gayatri, used a series of numerical relativity waveforms, which we do believe could capture this behavior, and essentially did a parameter estimation study with that. The problem there is that one, I mean, it's an 8-dimensional parameter space, or sorry, 9-dimensional parameter space. You have the eccentricity of the two masses and the 6 components of the spins. And numerical relativity waveforms take a long time to generate, like on order of maybe a week. I'm not sure what the state of the art is, but ballpark about a week of HPC time to do a single run. And so they only had about 300 models to cover this parameter space. And so there you have to wonder, like, how well is the parameter space being covered? How well is the comparison being done? Just because it's very, very difficult to completely cover the space using numerical relativity waveforms. I'm also personally skeptical of that result, or not the result, but some of what they suggested, because the eccentricities they showed were actually very large all the way up until the last stable orbit. My astrophysical prior says that it's very, very difficult. It's hard enough to get these things close enough to where they emit a burst of gravitational waves right off the bat. It's very, very difficult, though. You have to essentially have an almost head-on collision of two black holes, like almost up to the Schwarzschild radii, have a head-on collision to get eccentricities that large, that late in the in-spiral. And so, I mean, it's possible that it's, for instance, not the stuff that I studied or something that none of us have considered, but astrophysically, my prior is somewhat alarmed by that result.
Thank you. Any more questions? There's a question by Craig Henke. Is it right to say that there's a lot of degeneracy in the modeling of waveforms with eccentricity, etc., versus precession?
I think there is a lot of degeneracy. So I think, I mean, it's hard to write down. It would be hard. It's hard to do even the post-Newtonian problem in any way that we currently know of, because I think it's a very difficult. I think that's a very difficult. I'm not an expert in post-Newtonian theory, but I think that's a very difficult expansion to do, and then to convert back to some sort of waveform template. But I think even in the waveforms themselves, that there is a lot of degeneracy. So even if you had a perfect template, I think you might still see double peaks in the, or multiple peaks in the eccentricity and spin space.
Any more questions for Carl? I have another question regarding the Hege's law you mentioned when you have the third body coming, and you said that there's basically the binary will shrink to match basically the energy of the incoming or the velocity dispersion of the incoming stars. Is there a limit to how small you can shrink to something like equipartition, or you can always shrink more?
No, so it's actually much stranger than that. What Hege's law is actually arguing is that equipartition is actually impossible. So so this is where what's really weird. So if I have some binary, what Hege's law says is that if the incoming velocity is, well, it's actually expressed in terms of energy, but if the binding energy of the binary is sort of greater than the absolute value of the binding energy is greater than the energy sort of the center of masses of the two particles, then on average the binary is going to shrink due to each one of these encounters. The converse is true. The converse, however, is also true. If the energy of the binary is less than the sort of encounter energy, the binary will essentially widen. And eventually it will widen until the binary is disrupted. So what Hege's law is actually saying is that binaries will either continually shrink due to encounters away from sort of the typical energy of the star cluster, or they will widen until they are completely destroyed.
Okay.
And so so numerical results show that, typically speaking, you lose about 20% of the binding energy during, or you change the binding energy by about 20%, it's negative. So you decrease the binding energy by about 20% during each one of these sort of encounters that characteristically shrinks it. It's one of the weird things about stellar dynamics, because these systems are technically these gravitationally bound systems will never reach energy equipartition. They'll strive towards it. The star clusters themselves will strive towards it. They will never reach it. The binaries themselves will never actually enter sort of energy equipartition, because they will essentially shrink without limit. Eventually, they will shrink to the point where either the binary itself begins to interact tidally, or the binary black hole will merge due to gravitational waves, or the whole thing just gets kicked out of the star cluster.
Yeah. So basically the answer is that you can always shrink it more and more, and then some other process kicks in. Okay. Yeah. That was very interesting.
Yeah. There's a somewhat weird sort of, unsweet spot though, which is where you can shrink it enough to where the encounter timescale with third bodies is sufficiently low that you won't get another encounter for a while, but not so much that some other process kicks in. It's similar in a lot of ways to what used to be called the final parsec problem for supermassive black hole binaries.
Okay, any more questions for Carl? There's another one from Craig Henke. Do you think there is now strong evidence for a fraction of mergers having negative chi-effective, and thus for misalignment of spins and orbits?
Yes, I think there is, and the LIGO Virgo collaboration, which I'm not a member of, at this point agrees with me. Unfortunately, I didn't quite get to the end part of this talk, which is where I was going to talk a little bit more about the latest LIGO Virgo results, because one of the things that they finally got enough data to do in their latest data release was actually model the distribution of spin orbit alignments versus anti-alignments. And what they found was that, depending on how you look at it, anywhere from about, I think at the 90% level, 12 to 44% of the binary black holes that they've observed so far probably have negative chi effective, which means at least some amount of spin orbit anti-alignment. Now, if you take that to its logical conclusion and assume that those events were only created by dynamics, which is a bit of a strong assumption, but not an unreasonable one, then it suggests that anywhere from about 25 to 90% of LIGO's binary black holes are being formed dynamically. Now, there's one big caveat there, which is that LIGO is also more sensitive to heavier black holes. LIGO can see more massive black holes to a farther distance, so it's sensitive to a larger volume of space. And so, for instance, the globular star clusters that I studied a few years ago preferentially produce larger black holes, typically 20, 30, 40 solar masses, because they typically have lower stellar metallicities than a lot of star formation happening in the local universe. And so LIGO is actually, even if globular clusters only produce about 10% or so of LIGO's events, they would be about 50% of the detections. Or sorry, if they only produce about 10% of the underlying population, then they would still contribute about 50% of LIGO's detections. So you have to take the sort of mass, the mass weighted sensitivity into account.
Any more questions for Carlo? So I have a final question of my own. When you were talking about the fact that predictions for merger rates from dynamical environments are parameter free, you were showing a dependence, I believe, on the number of stars in the cluster. I don't know if you could go back to those plots. So I was just wondering whether there's, are these clusters like a one parameter sequence as well, or is there some like radius versus mass that evolves with time?
Yeah. So that actually does get back to the caveat that I had mentioned that I was hoping to get into, but unfortunately didn't, which is that most observational evidence suggests that the masses of these star clusters, roughly speaking, follow a 1 over m squared power law. But the radii are a little bit harder to pin down. And that actually very strongly determines both the overall evolution of the cluster and the number of black holes that it produces. And so that we don't have nearly as good of a firm handle on, sort of what the internal structure is of the cluster right at the point of formation. I'm working with a couple of galaxy modeling experts, Mike Grudich and a couple of other members of the FIRE collaboration, to try and sort of zoom in on that using high resolution models of galaxy formation and particularly cloud collapse simulations. But that's still some work in progress. Because that actually, if you make different assumptions for the initial radii of these clusters, you can change the results by an order of magnitude.
I see. Okay. Yeah, that explains this. Thank you. So I don't have any more questions. So Joseph, if there are no more questions, is that is Joseph here?
Yes. So thank you very much. So yeah, if there are more questions, we'll close the recording and then we'll finish the talk.
Yeah, we can thank Carl again for those who still have the microphone in. So thank you again very much for coming and giving us a talk, and best of luck with everything in Pittsburgh and or wherever you are subsequently. Yeah. And
no, thank you all so much for having me. He wasn't able to be in person, but here's looking to the future.